So I'm Shashank. I lead the data science team here at Monster, and we work on a variety of data science problems to help improve both the candidate as well as the employer experience who interact with the platform in the marketplace that the Monster has to offer. Before we get started, I also want to have a big call out to both the Geoawesomeness as well as the Travel Time team. This is personally my first time being on the sessions hosted by Geoawesomeness, and they couldn't have made the process much easier for an onboarding and just making sure we have everything we need to get started. So continuing on the great history on location shared by Charlie, the sequence couldn't have been better because Monster was amongst the first site to take the jobs from the classified ads and put it onto a website that people can search. And that's how the business at Monster started, where a lot of jobs were posted in local newspapers as classified ads. And what Monster did was to take those ads, put it up onto the site so that not just the people from that locality could look for that, but also people from different locations who are looking for the jobs in those specific locations can search for them and eventually apply to them. So that was a great start to the sessions, and I like how organically it flowed into what I have to share today. So what I'm looking to share today with this group is how we run job recommendations, and more particularly how we take location information into account to be able to serve the right jobs. A quick overview on the data science team here at Monster. So like I said, we work on a variety of different problems, both helping candidate and employers, which includes job recommendations. We also score quality of jobs that are ingested into our platforms. We also do machine learnings to impute missing informations. We are responsible for delivering an end-to-end solution, so not just running on POCs, but we do also deploy the solutions that are then integrated with the product offerings. And finally, we are a team of 7 strong people that includes data scientists as well as machine learning engineers. And we pretty much operate as in a software engineering team in a 2-week sprint cycle. We are looking to add a new team member to the team, so reach out should that be of an interest to what we do here at Monster. So one of the things which is at the heart of what Monster does is finding the right fit. Again, job, as much as any other thing that's out there, is very personal to an individual, and people are coming from all sorts of walks in their life. And what is their next best role is pertaining to the information that someone as an individual shares by themselves. And so I tried to break it down into 3 different problems, or 3 different challenges or pillars, whatever we call. But running your recommendations, particularly job recommendations, is unlike the recommendations that we may have come across conventionally by Netflix, by Amazon. It's not so much like that as it's much like a dating app. What I mean by that is recommending a job comes with its own set of specificity, in the sense where candidates are looking for a particular role and not just any role available that's out there, depending on the phase in career that they are in. And not just the occupation or the title, they are also looking for the jobs in a particular location. So that brings in a lot of specificity into what we can and can't recommend as jobs to the candidates. The second pillar and the challenge is the dynamic nature of the problem. So like I said, unlike Netflix and Amazon, where the items and products can be recommended through a variety of different users over a long period of time, unlike that, the jobs in the systems, they expire until they are either filled by someone or they are no longer posted on the job board. So we always have a flux of jobs that are active that goes expires. So there is a lot of dynamic nature in what can be recommended at what time. And finally, the problem is sort of a reciprocal in nature, in the sense where, well, on one hand, the ultimate goal for the recommender is for the user to see the job, click on it, and apply. We don't consider it to be an ultimate success because the ultimate success is an employer taking that application, interviewing the candidate, and finally hiring that person for the role. So when we think about recommendations of job, we not just take into account how likely a user is going to be clicking on the job, but there's also a distribution as to how many applications are going on a particular job to not essentially be in a situation where there are thousands of profiles applying to one job. And we know there's likely going to be one or few candidates selected for it. So we look into that distribution as well, which is more close to, again, as what you would find it on a dating app. So, like I said, it's not so much as a Netflix and Amazon, it's more like a dating app where we're trying to find the right fit for who you are with an ultimate success that you're getting hired for the job that is being recommended to you. So how we do it? We essentially, this is a 10,000 feet view I'd like to call, where we start with a candidate and a job. And while we know a lot about a job, what the job title is, where it's posted, what the description of the jobs look like, we make a bunch of inference for the candidates on whom we are recommending these jobs. And that inference comes in from a variety of different data sources in the form of the resume information, what role they've been in already, what education do they have, what skills they currently possess through the experiences that they've had, but also the interactions that they're having with the platform. Because when anyone is engaging with Monster, we know the type of jobs that they have viewed, the type of jobs that they've applied to. So using all of that information, we infer what is the desired job title for a given candidate is. What are the desired job location or locations, and what are some skills? And once we have this inferred information, both on candidate and job, in a nutshell, what we do is we represent this, I would like to say, a human readable information into a set of vectors. Now, vectors essentially are nothing but an array of numbers that represents the information that they are supposed to be representing. So we convert the candidate information that is inferred into a length of vector. We convert the information from the job into a vector, and we use a distance-based metric to then run the similarity to say how good of a match a given job is to a given candidate. And now you can imagine we have millions of users, millions of jobs, and all of these computations are happening in the backend. Then being able to find here are the best fit 10 jobs for any given candidate. So for that matter, any number of jobs, because we would have the distance metric measured for all the jobs across all the profiles. Now, what I'd like to focus on in today's session is this location information. So now we know we have this textual information. We want this information to be in the vector that represents both profile and job. So how do we go about taking this textual information and getting it into the numbers? And so there are a few different ways conventionally used from the data science perspective that we can make use of it. And they've got their own pros and cons. So off the bat, we can start with one-hot encoding. Let's take the location, do zeros and ones, and use that as our numeric vectors to represent the location information. It certainly is simple and allows the location information to be used as a feature. It comes with a significant cons that essentially could jeopardize the stability of the system. The first thing that comes with it is a curse of dimensionality. So imagine you have millions of profiles, and all these profiles have a variety of location information. In the worst case scenario, if all those million locations are unique, you're looking at a million dimensions. If not, certainly in tens and thousands of dimensions to be able to handle by a problem. Second, even if we try to figure that dimensionality piece out, it still has the limitation on semantic relationships. And what we mean by semantic relationship here is that, for example, take location Boston, Massachusetts, and New York in New York State. Now you could one-hot encode that information, and once it's one-hot encoded, you don't know if Boston and New York are close, and say, let's throw in the mix Los Angeles, you would have a one-dimensional vector for that. We wouldn't know if Boston and New York are much closer than, say, New York and Los Angeles. So that's what we mean by semantic relationship in the scope of location. We would lose that by doing it through one-hot encoding. And finally, we wouldn't be able to handle the different granularity of information in terms of location that we collect. Not every user is giving us an information at the city level. You would see users having their preferred locations as in state. Some would have it as a city. And to an extent, some would have it at the zip code level. So as we go from different granularity, we would eventually doing one-hot encoding on all those different levels, causing again the problem of dimensionality and losing the semantic relationship. So let's say we don't do it one-hot encoding and do a text embedding, which again, with such a significant progress being made in how we embed textual information through NLP models, we could take a location and embed that into a fixed set of vectors. So that solves the dimensionality problem because we know the information as an output is always going to be a fixed vector, but it still keeps the problem open on the semantic relationships, how close are two locations. And also it's sometimes tricky depending on the algorithm we choose to encode or embed the information. It's tricky if there is an unseen location that you may not have seen in the model training process. So to overcome both of this situation, we have come up with a two-step process where we take the raw location, and what I mean by raw location is just the text that pertains to a location information. We would get it passed through an API to get the lat-long information pertaining to those locations. So in this particular case, we have Boston as a location input for a user and in New York for a job. And what API gets us to is a centroid of pertaining to a lat-long for both Boston and New York. And in the second step is what we represent the lat-long into a vector that is of a length of 3. And while on the surface, it solves the key problem we have, which is how can we get the location information to in numbers. But what this also does is these 3 digits that are all pertaining to a vector, both for profile and for job, maintains the semantic relationship. And how it does that? So basically what we do is once we have the lat-long, we transform that lat-long into a 3-axis Cartesian coordinates. Now, you can do that on a sphere that has a radius of an Earth, or you could do it as a unit level sphere. So again, the dimensions of the sphere are not so particularly necessary for this transformation. You can do it for any application. And you can always come back to make it on the scale of what the Earth dimensions are. What we essentially do is take the lat-long and transform it into an X, Y, and Z coordinates. And those X, Y, and Z coordinates are what we call as our vectors of size 3. So what are the benefits for doing this? Like I said, it integrates well with the rest of the vector representation that we have for the textual information. It also solves the curse of dimensionality because you're always going to have 3 dimensions for any locations that you're trying to encode. And it does maintain the semantic relationship, which was the key requirement we had as we embark on the journey of solving this. So if you take a look at a few examples, so in the top table, what I have is the raw location information and a journey as it passes through the system. So for each Boston, New York, and Los Angeles, we have the corresponding lat-longs. Next, what we have is the transformation into the Cartesian coordinates, which again is a representation of X, Y, and Z for each of these locations. And as you can see, not only just it's in number, But the next column, there is a cosine similarity to be able to say, okay, what's the similarity between Boston and New York? And that similarity comes out to be 0.998 and so on. And when we compare that same similarity between Boston and Los Angeles, it drops down to 0.79. So not just it's getting us the numbers, but it's getting us that semantic relationship that we want to maintain. And the beauty of this is once you have the similarity, you can always go back into distance. So using now the dimensions of Earth, here is a small formula, I have it down below. But once you have the similarity score, you can transform that into the distance between these two locations. Now, keep in mind, this distance aren't necessarily the travel time distance or the commute distance. It's essentially connecting two different dots. But what we have found is it's often within the tolerance of 10 to 15%, which suffices the need that we currently have to be able to recommend location relevant jobs. But as you can see, going from a similarity score of 0.9988 something between Boston and New York, when we transform it back into distance, we get a value of about 190 miles. And similarly, when we do that for Los Angeles, we get the distance of 2,500 or 2,600 miles. And how it comes down to as it applies to the job recommendations. So I have a very basic bare-bone example here. Say there is a profile who is looking for a data scientist job in Boston, Massachusetts. And we've got about 3 different jobs, one in Boston, one in New York, and one in Los Angeles. And as we use the combination of the textual information as well as this location information, and then run the similarity, we get to know that the Boston one is the best match job. It's exactly matching what the user intends to find in the next role, along with the New York one, which is slightly on a lower end, given it's far from their preferred location, but it's still within the range depending on who the user is. And the Los Angeles one with the lowest score, given it's way far from what the desired location is. So while this is something we use on the recommendation side, the beauty of this transformation is you can now take location information and can use for technically any machine learning problems where you want to use locations as features. Because again, end of the day, what you're getting is X, Y, and Z. And if you are mindful of what this feature means for the problem that you're trying to solve, it certainly can be applied to either a problem of classification or regression, because end of the day, these are just the features. And with that, I am on my thank you slide.